Hi everybody, please do this problem. Amazing job. I knew you could do it. I knew you remember the formula. Tau, torque, is RF sine theta. It's super important for this unit. But we'll focus on the R and F. For most of this lesson, we'll assume that theta is 90, so R and F are perpendicular, and then it's just R times F, no sine theta. All right, let's watch a quick video. You might have seen something like this on TikTok a few years ago. I don't have any comments on it, but we'll just take a look.
It's called the Chair Challenge, and it's really baffling people.
Yeah, take a look at this video that has 7.5 million views on Facebook. It's from a Utah radio station, Planet 105.1. You see a bunch of girls picking up a chair with their head against the wall. The thing is, the guys can't do it. They can't stand up.
Right, so of course we had to give this a try. I mean, it's just what we do here, so take a look.
The chair challenge is more than picking up a chair. First, you start with your feet together against the wall. Next, take 2 steps back in a straight line, put your feet together, lean forward. Your head has to touch the wall at all times. Slide a chair in, pick that chair up, and try to stand up. And let's see how we did. Danielle? Got it. Holly? No problem. Maureen? Those leopard heels didn't stop her. Then it was my turn.
All right, the true test.
You gotta touch me. Are you serious? You can't do it for real? You stand up. Just stand up. Stand up. Just stand up.
I can't.
Yeah.
You guys are even heckling me.
I mean, and truly, you could not do it.
No, and I wasn't alone. Look, Austin, Austin's really upset about this because he thinks he can do everything.
Right.
He couldn't do it. And our
Austin's still
custodian,
like,
Dwayne, he tried. He couldn't do it either.
Right, so what's the deal? You might be kind of curious. We turned to physical therapists at Metro Health for answers.
Some people think it has.
Okay, you guys probably got the idea. Side note, if you guys use TikTok, that's fine, that's your prerogative. But just be aware if you use or support multinational corporations such as TikTok or evil companies known as Zoom, you are kind of supporting them and what they believe in. Something to be aware of in your life. I'll just close this tab. Oh, whoops. I'll close this tab too. Oh man, I have so many tabs open. I gotta close them all. Okay, now we gotta go back to lesson. So the video, in general, men have larger feet than women. So it could just be a factor that the men were farther from the wall. But this is general, not always, but generally, men tend to have more upper body muscles than women, and women tend to have wider hips so they can more easily give birth. So what often happens, as you could probably see, is that women have a lower center of gravity, or center of mass, than men. So let's just say we have a man here and a woman here. The man's center of mass might be right here. The woman's center of mass might be right here. How would you know? How did you figure it out? You can find your center of mass. It's a nice practice problem we might do tomorrow. By taking the person, turning them sideways, and don't put them on a scale. Put them on 2 scales. These are not like dynamite plungers, they're scales. So let's say hypothetically, I have two people and they both have the same mass, 100 kilograms. And let's round. Let's say G is about 10. I know it's 9.8 meter per second squared, but we can round to 10. If these people are both 100 kilograms, if they were both on 100 kilograms is about 1,000 newtons under this assumption. So if either person, this man and this woman, stood on a scale, the scale would say 1,000 newtons. But now they're on two scales. How will these readings be different between the man and the woman? They both have to add up to 1,000, but what do you expect to see in the difference? Both scales for both people have to add up to 1,000 newtons, because a free body diagram would say, oh, there's one force of gravity going down, two forces from the scales pointing up. But there will be a slight difference. Not a very big difference, but slight. If this is the woman, the scales might say something like 550 newtons and 450. That adds up to 1,000. The man's scales, they'll still have the same sum, because in this example, I said they have the same mass and same weight. But the numbers, if the man's higher center of gravity is on the right side, there'll be more force on the right side. So this might, again, the difference is very, very small. The difference is probably mostly due to foot size, but it might be 570 newtons and 430. So the sums are the same. They both add up to 1,000 newtons, but more of the man's mass is higher up on his body. More of the woman's mass is lower down on their body, but it's actually an extremely small difference. What's the point of this? I'll tell you. We can solve a whole bunch of problems by combining two equations. Newton's first law for forces, which is whenever the net force equals 0, and also Newton's first law for torques, when the net torque is 0. If an object is in equilibrium, this is true. And if you think back, we actually did this twice. We used to do the net x force and the net y force equals 0. Today's lesson is all about adding one more idea. The net x force is 0, the net y force is 0, the net torque is also 0 if they're in equilibrium. If an object doesn't just start rotating for no reason, you know, there's probably no net torque on it. Most bridges and traffic lights and hanging signs in the world are not always spinning all the time. They're usually stationary at rest and they never start spinning. So for most objects in life, the net torque is 0. And we can use that to solve a lot of things, like these forces. If you didn't know about torque, you could never figure out which force goes where. You would have no idea what the two forces are, because you know they add up to 1,000. But there's two unknowns and only one equation in the net y force. You couldn't solve this. But using torque, you can. So we'll do a much simpler example, and we'll talk again about center mass. So again, let's say we have approximately me, I'm 100 kilograms, and I am on a 100 kilogram log. I chopped down a big tree, and it's also 100 kilograms. All right, and let's say I use this tree to make a bridge. Okay, perfect. 100 kilograms, 100 kilograms, 200 kilograms. The total weight of the system is 2,000 newtons. If I'm exactly in the center of the log, and the log is perfectly symmetrical, how much force would each side of the hole, would each cliff, apply upward? So there's two forces. Let's call them FL for left side and FR for right side. If I was right in the middle of the log and the log were perfectly symmetrical and uniform, what would FL and FR be? If everything were perfectly symmetrical, FL and FR would be the same, 1,000 newtons. The sum is 1,000 to balance out this system. So 1,000, 1,000, that makes it work fine. Great. But what if that were not the case? Let's say it's like a 4-meter long chasm. I know probably a 4-meter long log wouldn't weigh 100 kilograms, but let's go with it. Let's say I'm only 1 meter from the left side. But I'm still 100 kilograms. Now, which one's bigger, FL or FR? Hopefully you can tell. The center of mass is now on the left side. The center of mass of the knee log system is on the left side, somewhere in here. We're not sure where. But the center of mass is somewhere in here, toward the left side. That means there's more force from the left side, because there's more weight there that needs to be held up. But how can we figure it out? How can we find FL and FR? It's impossible with just forces. We can only use the net Y force equation. So FL plus FR equals 2,000. Newtons. But we can't use X forces. There are no X forces. We're assuming it's all vertical to make things easier. We have to use torque. We have to realize the net torque is 0. Hopefully that's true. In most bridges, you don't want them to fall and rotate while they're working. You want them to stay stationary in equilibrium so you can cross them without dying. But let's solve. The trick is we have to pick a pivot point and an axis of rotation. This is a really important idea. The pivot point is not in the middle. That's not good. We don't want that. We can pick where the pivot point goes. It could be anywhere. That might seem kind of strange. Most people say, oh, it's a linear, uniform thing. The pivot point must be the center, because it's called radius. Radius is from the center. You have to break your mind free of that assumption. Yes, this log is not rotating around the center. So you are correct. The net torque around the center is 0. But the log, I can probably use camera magic. Oh my gosh, this is a great lesson. Yes, the log is not rotating like this around the center. But is the log rotating like this around the right side? Also no. Is the log rotating like this around the left side? Also no. No matter where you pick the pivot point, the net torque is 0. And for a certain reason, it's much, much better to choose the pivot point being here than it is to be here. See if you can figure out why. The right side's okay too, but we'll start with left side. Putting the pivot point here is much better than putting it in the center. See if you can tell me why. Let's try it. The pivot point's at the center. So what are the torques? Well, I'm applying a torque. My torque is RF. Real simple. No theta. And let's skip over G. We're still using G equals 10. 1 sig fig. So if I'm 100 kilograms, my weight's 1,000 newtons. So the first torque, 1 meter, times 1,000 newtons. That's good. And let's make it negative, because my torque will turn the log clockwise, which is the negative direction. Let's put in the log's torque. The log's torque is applied all over the log, but we can treat it as all of it's in the center. It's still a uniform linear log. So pretend the whole 100 kilograms, or 1,000 newtons of weight, is in the center. So it's again 1,000 newtons. 2 meters, because that's the center of mass of the log. And also negative, because that is a clockwise torque. Well, we have a negative torque and a negative torque. We must have a positive torque. Look at the problem. It's Fr. Fr is applying the positive torque. The radius for Fr is 4 meters. So 0 equals negative 1,000 minus 2,000 plus 4 Fr. Fr equals math stuff. It's just 750. That's easy. It's just 3,000 over 4. Yeah, 750. Okay. Yeah. This equation has only one unknown, Fr, so I solved for Fr. I got 750 newtons positive, which is upward, which works out nicely. Makes sense. Sounds good. Well, it probably would have made more sense to make these negative because they're down, but whatever. It's fine. It's fine. It's fine. Notice, I didn't include the torque for FL. Why didn't I have another term for the torque around FL? Tell me. Oh, wow, yeah, good job telling me. Good job. If you put the FL term you gotta multiply by R. I remember we picked the pivot point to be the left side. If you pick the pivot point to be the left side, the force on the left side is applied at R equals 0. This is how we made the problem solvable. This would not have worked out if you put the pivot point in the middle, which is why I told you not to do that. If you put the pivot point on an unknown force, that force causes no torque, and we could ignore it. You see? And then we can easily find the last unknown. Great job. So to make these problems easier, if there's 2 unknown forces, but the object is in equilibrium, say, oh, the pivot point's right here, so this force causes no torque. If you want to find FL, you could put the pivot point right here. Then FR causes no torque. And that's cool, that's great, that works. But there's an easier way. Throw this in here. If FR is 750, FL is 1250. That works out. FL plus FR is 2000, and FL is greater, which we said must be true. So, good job me. I can check really fast just to be sure. if I do this in my head, on the right side, it would be negative 2,000 minus 3,000. 5,000 equals 4. Yeah, it works out. I did it. Good job, me. Cool. So this is a bridge problem where you know the net force equals 0 and the net torque equals 0. The very subtle trick, choose the pivot point to make the problem easier. Don't make the pivot point in the center. Make the pivot point the location of an unknown force. Then you don't need that force in the equation. This might be a little bit tricky. There's a lot more stuff to do. We'll probably come back to this tomorrow. But an equilibrium problem, a statics problem, you can say the net force equals 0 and also the net torque equals 0. And that gives you more equations to play with to solve. Cool. Just because it's in this chapter of the book, I also have to review these problems we used to do. You see these problems where there's like a box hanging from 2 strings. And in case you guys forgot, this is how you do it. So the x components would be f1 cosine theta 1, f2 cosine theta 2. So it would probably be like negative f1 cosine theta 1 plus f2 cosine theta 2 equals 0. That seems good to me. And the y, they don't add up to 0 because they have to hold up the box. So f1 sine theta 1 plus f2 sine theta 2 minus fg equals 0. That's how we used to solve them. I'm pretty sure there's a shortcut. I actually only just thought of this, but I think you can find it easily if you treat it as a torque problem around this point. We'll do it tomorrow, I think, in class, and we'll see if it works out. But there should be a nice shortcut if this is too long, now that we know torque. I just had to show you one more thing. Another very common problem is this problem. There's like a we got a cliff, we got a log, the cliff continues upward. Okay. So here's the problem. It's what do you call it? It's like a sign, just like a sign hanging from a stick. Yeah, sure. Okay, I'll just show you this in what I'm doing. So there's a stick with mass 0. There's a box with mass m, and there's a rope here. You want to find the tension in the rope, assuming this stick is called a boom, B-O-O-M, boom, is rotating, could rotate freely, so it would fall down like this because of the weight, except it's held by the rope. So to solve this problem, we need to find the force of tension around the pivot point. In this problem again, don't put the pivot point at 0, at the center. Put the pivot point right here, because that way the object will actually rotate around. You could put the pivot point here or here, and that would be interesting. It would help you solve for more unknowns. But to set this problem, you have to be careful. There's two different R's. The torque from the rope will be R1 Ft, and there is a theta. This is theta. The torque from the mass would be no theta. The theta is 90, sine theta is 1. So this you could use to find F2. That would be fine. There's an interesting thing about this problem. What if this boom, the stick, weren't attached here? What if we just like erased it? Well, it would collapse, it would fall. It would fall apart. This location here, this attachment, there's two forces. In this picture, I think the force from the hinge or from the pivot or from the axis would be like this. And also, we need another up. We need another downward force. Downward force. Fx, Fy. That's a little confusing. I'll probably talk about it in class. But these two forces also exist. We put the pivot point right here, so we can ignore them. But if you were asked for them, you have to move the pivot point or use Ft. I'll show you an example in class. Sorry for going a little long. You'll be okay. Split this video in two. Go back in time and split the video in two parts if it was too long. And have a nice day.